Okay, so let's look at RSA encryption. The concept behind it, some of the mathematical machinery that we're going to be using, and why it works, sort of what is it, and then we'll do examples in the upcoming videos. Here we have Bob, and here we have Alice and their friends, and Bob wants Alice to be able to send him a message, knowing that it's going to be intercepted by this horrible person, Eve, in the middle here. And as you can see, she's just dastardly. She's going to intercept anything that Alice sends to Bob. They have an insecure channel. And so the idea is, the question is, how can Alice send something to Bob? Eve will see it, Bob will see it, and Bob will be able to figure out what the message is, and Eve won't. What is the way that they could do this? How could they communicate securely over an insecure channel? And the answer is number theory. So Bob is going to take two large prime numbers, P and Q. P and Q are going to be large primes, and these will be hundreds of digits in practice. The ones that we're going to use for this are going to be small. They're going to be 1 or 2 digits, the ones that we can do the examples by hand. But Bob is going to have to pick very large ones, because the key to this is that the number n, which is P times Q, and this is going to be part of Bob's public key, what he's going to send to Eve, or to Alice, also Eve, right? Eve is going to get it. But Alice is going to be the recipient of this. He's going to send her P times Q. N is going to be extremely hard to factor for large primes P and Q. It's going to be computationally infeasible to factor N. The largest computers in the world, if you pick the primes large enough, if you pick these primes P and Q to be big enough, will take like years or thousands of years or something to factor N as a product of primes, or end of the life of the universe or something. If you make them big enough, the computational, even with the most powerful computers, the computation just becomes unworkable. And so, especially if this is like a war or something, and you only need the message to be, that we're attacking at this time on this day in this place, and then after the attack, there's no point in having the message because everybody knows about it. Especially in a situation like this, where the message doesn't have to last forever, so to speak. The fact that Eve can't factor N quickly and efficiently is the key to public key cryptography, to the RSA public key crypto system. So Bob sends N and this number E, and we're going to talk about this directly. This is called the public key. This is the public key. He publishes this, so he sends it to Alice. Eve gets a hold of it. What is so special about E, though? By the way, E is called the encryption exponent, and it's because Alice is going to use E to encrypt her message. But can Bob just pick any E? No. Well, he needs to pick E so that the GCD of E and P minus 1 times Q minus 1 is equal to 1. The greatest common divisor of E and the primes P minus 1 and Q minus 1 has to be equal to 1. And why is that? That is so that he can compute E inverse, which we're going to call G mod N. And why is that? Why does he need E to be relatively prime to P minus 1 times Q minus 1? It's so that he can compute G so that G times E is congruent to 1 mod. Actually, you know what? I think... And why is that? Why does he need E to be relatively prime to P minus 1 times Q minus 1? That is so he can compute D so that D times E is congruent to 1 modulo P minus 1 times Q minus 1. Because E is relatively prime to P minus 1 times Q minus 1, he can find its modular inverse, right? It has a modular inverse mod P minus 1 times Q minus 1. D is E inverse mod P minus 1 times Q minus 1. And if you're at all confused about this, you're like, wait a second, what are you talking about this? Why is this? Or what are these things? Please do check out the videos on that, on modular inverses and divisibility and the GCD and the Euclidean algorithm and all of that. all of that cool stuff that we need for this video. We're assuming in this one that you already know all of that stuff, and also Fermat's little theorem, which we're going to be using shortly. Okay, so Bob computes n, which is p times q, and e, which is relatively prime to p minus 1 times q minus 1. He sends that to Alice over here. And what does Alice do? Well, she gets her message. M is her message to Bob. How does she get the message? She takes what's called her plain text, and that would be the English or whatever language we're communicating in, the natural language message. So, hello, how are you? I'm Alice. You know, Eve can't read this. She's so dumb. Whatever. She encodes this as a message we do call it the message. That's a bit deceptive because m is a positive integer. M is a natural number, and in particular, we're going to have m has to be less than capital N. Of course, it's going to be bigger than 1. You can't really encode a message with just the number 1 very easily, but it will be bigger than 1. That's important for the modular arithmetic that we're going to be doing. And it's also got to be less than n. It has to be less than n. And we'll see why when Bob decodes this thing. But first, Alice has to encode it. She has to use the encryption exponent e to encode it. How is she going to do that? She's going to compute m to the e modulo n. And what does this mean? What is m to the e mod n? You might be used to seeing something with the 3 bars is congruent to something mod, and you might not have been used to seeing this one. This means the remainder. This means she reduces m to the power of e modulo n. So she computes the remainder that you get when you raise m to the power of e and then reduce it modulo n. She does that, and that is what she sends to Bob. This is the thing that she sends to Bob, and Eve sees it, right? Horrible Eve sees this as well. So Eve can see this, and Bob, the intended recipient, can see this, but Eve can't read it. Eve cannot read this. She cannot decrypt the message. Only Bob can decrypt the message. Why? Or anyone who knows what P and Q are. If you just know what N is and you just know what E are, you can't do it. But Bob, he knows what P and Q are. So while Eve is trying in vain to factor N as a product of primes, which she can't do it because it's computationally infeasible, Bob is computing D, the decryption exponent. D times E is congruent to 1, mod P minus 1 times Q minus 1. And why is this the decryption exponent? Well, or how are we going to use this to decrypt the message? Well, this means that D times E is equal to P minus 1 times Q minus 1 times K plus 1 for some K in the integers. For some K in the integers. DE is a multiple of P minus 1 times Q minus 1 times an integer plus 1. And this is what's going to allow Bob to decrypt the message. Because if he takes m to the e, so this is what Eve sent him. She sent him m to the power of e, and he raises this to the power of d. What is he going to get? Well, he's going to get m to the power of e times d. And e times d, of course, is the same as d times e, right? These are integers. Multiplication is commutative in the integers. So that's the same as d times e, which is the same as m to the power of p minus 1 times q minus 1 times k plus 1 mod n. Actually, you know what I'll do back here? I'll do the mod. This is mod n here. And then here I'll factor n as p times q. And why are we going to do this? Because we're going to see that this quantity here, this number, m to the p minus 1 times q minus 1 times k plus 1, that's actually going to be congruent to m. This is going to turn out to be, after some dots, we'll do a bunch of steps. This is going to turn out to be congruent to m mod n, or mod pq. And there's a d in mod. I'm pretty sure there's a d in mod. So this is going to be m mod n. So it's going to leave the same remainder as m when we divide by n. And this is why we needed m to be less than n. So it will be its own remainder when we divide by n. Reducing this thing mod n will leave the same remainder, dots will leave the same remainder as m modulo capital N, and this is going to be exactly equal to m, the message. That's the idea behind this. Okay, so why is this true? Why does this stuff end up being congruent to capital N? Well, what we're, to m mod capital N. Well, what we're going to show is that it's congruent to m mod p, and it's also congruent to m mod q. And then because n, and so what that means is that p divides something. Well, we'll see. We're going to do the steps in a second. But the idea is, without going into the details now, we'll do that in about 5 seconds. Being congruent to m mod p and being congruent to m mod q, because they are relatively prime, and we'll show this in a minute, is going to mean that they are that it's congruent mod p times q. And this is generally how we solve modular arithmetic equations with where the modulus is not prime, where it's a product of some primes or a prime power or something. Is you look at the remainders that it leaves when you divide by the various prime factors of that, and you sort of piece together a solution. Okay, so let's see how we do this. Well, m to the p minus 1 times q minus 1 times k plus 1, let's use our exponent rules. This is congruent to m to the p minus 1 times q minus 1 times k times m to the 1 mod pq. And that's just using our exponent rules. When we multiply exponents to the same bases, we add the exponent. So bringing out that 1 there. And then we have m to the p minus 1 to times q minus 1 times k. And why am I sort of coloring this different from that? It's because we are going to, in this next step, we are going to factor out the q minus 1 times k and use our exponent rule for exponents. If I raise m to the power of p minus 1 to the power of q minus 1 times k, what's that? Well, when you exponentiate an exponent, you multiply the exponents. So these things are equal. And then actually, we'll just write that as m instead of m to the 1, and this is all mod pq. And let's just maybe highlight this stuff appropriately. There we go, the q and the p, and that's the m. This is getting kind of monochromatic and hard to look at. There we go. Okay, but actually, let's keep these in different colors. There we go. Okay, and this is where we use, this is the fun part. Fermat's little theorem comes in. I always want to say Fermat's last theorem, but Fermat's little theorem is actually much more useful. Fermat's last theorem is the famous one. Fermat's little theorem, what does it say? It says that a to the p minus 1 is congruent to 1 mod p for any prime p. And this is what we're going to use here. This is m to the p minus 1. M to the p minus 1. So what can we say about m to the p minus 1? It's 1 mod p. We get m to the p minus 1 is 1 mod p. And so if you raise that to some power, if you raise 1 to some power, right, m to the p minus 1 to the power of q minus 1 times k, well, that's congruent to 1 to the power of q minus 1 times k, which is congruent to 1 mod p. So what does that mean? That means that, well, this stuff got, actually didn't get anything. It just looks like it got messed. There we go. That's perfect. This is m to the p minus 1 to the q minus 1 times k. There we go. That's m to the p minus 1 times q minus 1, or to the power of q minus 1 times k. That's 1 to the q minus 1 times k, which is 1 mod p. And so what does this mean from the definition of modular arithmetic? This means that m to the p minus 1 times q minus 1 times k minus 1 is a multiple of p. It's p times, I don't know, we'll call it s for some s in the integers. I don't know why it took me so long to think of that. When we usually use like p and q and r and stuff, and then we start to run out. I've already used p and q, and I'm getting all confuddled by this. I used my regular integer letters. Okay, there we go. M to the p minus 1 times q minus 1 times k minus 1. That's p times s for some s in the integers. And this is the key to this. We could switch when I factored out the q minus 1 times k here, right, and then did all this stuff with m to the p minus 1, show that it was used this to show that m to the p minus 1 times q minus 1 times k was congruent to 1 mod p. Well, you could switch the roles of q and p here, right? You could factor out a p minus 1 times k and keep the q minus 1 in here and get the symmetric result that m to the p minus 1 times q minus 1 times k minus 1, or I should do it, I'll do both the steps, is congruent to 1 mod q, and that will mean that m to the p minus 1 times q minus 1 times k minus 1 is equal to q times z for z in the integers. So there we go. We have these two things, and this actually I should highlight the q separately from the z to draw attention to it here. Let's put, that's the q, and then we have the z here. So what does this mean? This means that this thing, it's a multiple of p, and it's also a multiple of q, and since p and q are distinct primes, they're large distinct primes, GCD of p and q is equal to 1. This means, by the fundamental theorem of arithmetic, this implies that m to the p minus 1 times q minus 1 times k minus 1 is a multiple of p and q. It's p times q times, say, t for some t in the integers. And so if this is unfamiliar, if this step is weird, hopefully at this point of the video, I feel like the people who are still watching will have more familiarity, or will have gone back and watched some of the earlier, more fundamental videos. But this is just fundamental theorem of arithmetic, right? If this prime divides the number and this prime divides the number, then both the primes have to divide a number. So the best way to understand this, if you haven't watched the video, just want to quickly get an intuition for it, is if 7 divides a number and 5 divides a number, well, then 35, their product, right? Like PQ has to divide the number. It's not that way with composite numbers. If you have like 6 and 4, so 6 can divide 12 and 4 can divide 12. That doesn't mean their product 24 divides 12 because they're composite, right? They have these common factors that ruin it. So the idea is that this is the key step. We can conclude, because P and Q are prime, because they are relatively prime, they have no common factors. If each of them divides a number, then their product has to divide that number, which is the same as saying that so m to the p minus 1 times q minus 1 times k minus 1 is a multiple of pq, is the same thing as saying that it's congruent to 1 mod pq, which is mod n, of course, right? N is equal to p times q. That's where n came from. Okay, so we're in business. We can go back up here, all the way back up here to this point, and say, well, this thing times so what did we start with here? We had the message, the encoded message that Alice sent to Bob, m to the e. Bob raised it to the power of d. We did some mod stuff. We replaced it with p minus 1 times q minus 1 times k plus 1. We could do that because de was equal to p minus 1 times q minus 1 times k plus 1, because e was relatively prime to p minus 1 times q minus 1. Bob was able to do that because he knew pq, the factorization of n. So since p minus 1 times q minus 1 and e were relatively prime, there was a modular inverse for e mod p minus 1 times q minus 1. Bob computed that. By the way, I didn't mention, but you can use the extended Euclidean algorithm if you want to do that. And so check out the video on that as well to see what is the extended Euclidean algorithm and how we can use it to compute modular inverses. Okay, and then finally, at the end of all this, then we did all this stuff down here, and we found out that this is 1 mod PQ. So that means that m to the e to the d here, it turns out to be congruent to 1 times m mod PQ, and PQ, of course, is equal to n. Well, the thing jumped on me. There we go. This is congruent to 1 times m mod n, which is m mod n. And that is it. Bob now has, he computed m to the e to the d, and he reduced it mod n. So what this is saying is that this thing is congruent mod to m mod n. When you divide this thing by n, you reduce it modulo n, you find the remainder that it leaves upon division by n, that is going to be m. That remainder is going to be m. And so Bob can find the message, right? Bob up here has recovered the message. And I was going to I'll put a smiley face anyway. But Bob's already smiling. Bob's happy. He got the message. By reducing m to the e to the power of d mod n, because it leaves the same remainder. Because of Fermat's little theorem, extended Euclidean algorithm, modular arithmetic, modular inverses, all of this cool number theory stuff, and the fact that at present there is no way to efficiently factor large positive integers as a product of primes, or if the primes are large, it's very hard to factor them. If the primes are small, it's easier. It's not that you can just take any large number. You know, if you take 2 to the power of 500 or something, that's a large number, but you can factor it pretty quickly. But if they're large primes, and as a product of large primes, it's very hard to factor it quickly. And so Eve can't do that, or she can't do it in a reasonable amount of time. And this is how we can, and the reason I use the phrase, I was about to say, this is how we can share information securely across insecure channels. There was a very famous article where this came from, published, I think it's in the 70s. It's called "Secure Communication Over Insecure Channels," and this is the sort of, it's considered one of the things that was the birth of public key cryptography. So this RSA encryption is this really brilliant, really beautiful idea using fairly, I don't want to say it's simple math, because when you're learning it for the first time, it doesn't seem simple at all. But compared to how complicated math can get, this is actually very sort of simple and clean and nice, and not too bad at all. And when you compare it to what you get, modern computer security is based on this, right? The reason that your bank account information is safe, on the reason you can do secure online banking, is because of stuff like this. So it's really cool and fantastic. In the next video, we'll see. So we're going to see a slightly modified version of this, because it actually turns out that we could have been a bit more efficient. We could have been a bit more computationally efficient with this. The second that we come up with an algorithm, so this is proving the correctness of the algorithm. This is proving that the algorithm works. And then the next thing we think is, could we be more efficient with it? We're going to see it's efficient to have a smaller e, and if we could make the modulus here smaller, that might be helpful. So we'll see a way that we can use GCDs. We can use some divisibility stuff to generalize Fermat's little theorem, the FLT over here. We'll come up with a sort of generalization of this that we can then use to get some more algorithmic efficiency. And then we're going to have some examples. We're going to have some concrete examples. So the kinds of things where and those things, they reinforce the idea and they help you sort of understand it. This is the test. Do you really get it? Do you know what to do if we're trying to set up a cryptosystem with primes? And those are with particular primes. And those are actually the kinds of things that can come up on tests. And so it's always good to get some practice with those kind of questions. So we'll see you in the next video.